We're going to make a video now on derivatives. A tangent line is a straight line most resembling a graph near a certain point. So for instance, let's look at this first graph here. Let's look at this red point. If I said to you, what's the tangent line there? It would be approximately this blue line. That blue line touches the curve in only one point. Similarly, on this next curve, there's a tangent at that point, and in this next curve, there's a tangent at that point. Okay? Now, up until now, we've talked about needing 2 points to determine the slope of a line. However, as we begin talking about derivatives, we need to talk about the slope of a curve at a certain point, 1 point. So suppose we wish to determine the slope of the curve y equals f of x at the point where x equals a. This means we're going to find the slope of the line tangent to the curve y equals f of x at x equals a. Now, when x equals a, since we're talking about the curve y equals f of x, that means y is f of a. And so what we're really trying to do is find the slope of the tangent line to the curve at the point a comma f of a. So let's take an example, the one on the right of your screen there. There's a red point, we've drawn a tangent line. That red point is the point a comma f of a. A is an arbitrary value for x, and since it's on the curve y equals f of x, the y coordinate is literally f of a. To determine the slope of that line, we're going to need to determine the slope of a line connecting that point to another point on the curve infinitely close to a f of a. Well, how are we going to do that? Our process is going to be kind of interesting. We're going to, again, we're looking for the slope of that red tangent line. I'm going to get a point near the red, I'm going to get a point near the point in question on the curve. And I'm going to draw the slope in between those 2 points. And I'm going to use that as an approximation of the line in question. Now, you might be thinking, well, that's not a great approximation. I agree with you, it's not. But limits is going to help us, the concept of limits is going to help us do what it is that we're trying to do. So, how do we find that point? We start by finding a point that's a certain horizontal distance away from the point. So what I'm going to do is I'm going to say the second point is h horizontal units away from the first point. Since the first point has a x coordinate of a, the second point has an x coordinate of a plus h. And since it's on the curve y equals f of x, the y coordinate of that second point will be f of a plus h. And we're going to find the slope of that line and say that it's a rough approximation of the slope of the line that we're looking for. Again, not a great job by that diagram, but limits will help us. And so we're just going to literally use the slope formula, y2 minus y1 over x2 minus x1. And we'll do that over the course of the next few slides. So horizontal distance of h, the x-coordinate is a plus h, the y-coordinate is f of a plus h. We have it written right there. We draw that approximation line as I said we would do, and we determine the slope. We wish to determine the slope of the shorter tangent line, the one that I'm sketching in red right now. The approximation line, the second one that I'm sketching in red right now, that's just a rough approximation, but the slope of that second line, the approximation line, is f of a plus h minus f of a all over a plus h minus a. In other words, y2 minus y1 over x2 minus x1. And a plus h minus a will always simplify to just h. So we're going to use this right here as our slope formula in between the 2 points. Now, let's look at that green point. That green point has a different value of h. The horizontal distance between the point that we're interested in and the green point is smaller than the horizontal distance between the point that we're interested in and our original other point. Okay, so we're bringing it in a little bit closer. And when we do that, you see that second h value is smaller. When we do that, and again, we're trying to find the slope of this red tangent line here. When we do that, we see that our second tangent line, the one connecting our point with the one that's a little bit closer, that second tangent line actually becomes a better approximation of the line that we're trying to get the slope of. So here's the line that we're trying to get the slope of. Oh, wow, I did a bad job there. We're trying to get the slope of that line. Well, this next tangent line, this next line that I'm about to draw in between from the green point to the point that we're interested in, it's going to be a better approximation. And I'll show you on the next slide. There. And so what we can see is that as we get going here, we're going to see that if we can simply reduce that value of h, if we can reduce that value of h more and more and more, we're going to see that our line connecting those 2 points gets ever and ever closer to the line that we're trying to get the slope of. Okay? So the slope of the approximation line between AF of A and the green point better approximates the slope of the small tangent line than the slope of the approximation line between AF of A and the red point. And as we decrease that horizontal distance, we decrease the overall distance between the 2 points. Eventually, as h, the horizontal distance between the 2 points, gets smaller, the points get closer together, and the slope of that approximation line that I keep on redrawing better approximates the slope of the tangent line that we're trying to figure out, and that's that line right there. So if we could bring that second point infinitely close to AF of A, we would make the slope of the approximation line virtually identical to the slope of the tangent line. We know from many slides ago that the slope of the approximation line is given by the formula down below, f of A plus h minus f of A over h. And using limits, we can say that the slope of the tangent line will be equal to the limit as h goes to 0 of f of A plus h minus f of A over h. Okay? And that's the derivative formula. The derivative of the function y equals f of x is given by the formula f prime x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. And to reiterate, all that is y2 minus y1 over x2 minus x1. And remember, x2 minus x1 is x plus h minus x, and that always simplifies to h. So that's why there's only one term down below. Other symbols for the derivative include dy over dx or y prime. The derivative of a function allows you to determine the slope of the line tangent to a curve at a given point. In other words, you can find the slope of the line when you only know one point on the line. The value of the derivative is often called the instantaneous rate of change. So let's do some examples. We're going to determine the derivative of the function f of x equals x squared and evaluate that derivative at x equals -3. Before we begin, I just want to remind you of some function notation. If f of x equals x squared, then what I'm really saying is f of block equals block squared, and I can plug in an x plus h for that block, and I'll get x plus h quantity squared. That's something that's going to come up in a bit. But f of x will be x squared, f of x plus h will be x plus h quantity squared. Okay? So how do we begin our solution? Well, first thing we do is we draw we write down the formula for a derivative, and then we say it's the limit as h goes to 0 of x plus h quantity squared minus x squared all over h. That will equal the limit as h goes to 0 of x squared plus 2hx plus h squared minus x squared. remember when you expand out x plus h quantity squared, it's really, you're expanding, two brackets into each other and you're getting a middle term. Sometimes people mistakenly say x squared plus h squared, but it's not. It's x squared plus 2h x plus h squared. Okay, and so that's what our numerator becomes. Our denominator is just h. So we have the limit as h goes to 0. The x squared and minus x squared cancel out, so we're just left with 2hx plus h squared all over h. I can go up here and factor out the h from the numerator. I'm left with 2x plus h. I still have a factor of h in the denominator. I can now cross these out and I can sub in an h value of 0. 2x plus 0 is 2x. Something that sometimes throws people for a loop when they're first used to this, your derivative formula is going to have x's still in it because you're subbing in for h. You're subbing in the value of 0 for h. You're not subbing in anything for x. So don't be surprised if you have x's remaining in your derivative formula. So what that means is the derivative, this question was in two parts. Determine the derivative of the function f of x equals x squared. The answer to that first part is f prime x equals 2x. That's the derivative. The second part said evaluate the derivative of x equals -3. So to answer that, I simply plug -3 into the derivative formula and I get -6. So the derivative of x equals -3 is -6. Okay, so you might be thinking, well, what the heck does that mean? Okay, we got some information here, but put some context to it. So that's what the next question is good for. Let's determine the equation of the tangent line to the curve y equals x squared at the point where x equals -3. So this is the same as the last question, same function and the same x value. But now it's saying to us, give me the equation of that tangent line. So let's draw a graph. That's the graph of y equals x squared. It's that parabola there. And the tangent line to the curve at x equals -3 is this blue line. I want to know the equation of that blue line. I'm going to have to do some grade 9 math. Well, in order to know the equation of a line, I should know a point on the line from grade 9 math and the slope of the line. Well, I just figured out the slope of the line, believe it or not. The slope of that line is -6. So that's what the derivative is. It's the slope of the tangent line at that x value. So the slope of that tangent is -6. All I need to do now is figure out what is a point on the line. And to do that, I already know the x value of this point. It's -3. I'd like to know the y value, and I simply plug it in to the formula for the curve. The formula for the curve is y equals x squared. So literally y will be -3 quantity squared, which is 9. So what I've got is a straight line going through the point -3, 9 with a slope of -6. I can figure out that using my grade 9 math skills. Oops. So going back to there, what I'm going to do is I'm going to say y equals mx plus b. I'm going to plug in a slope of -6. That's what the m is, -6x plus b. I'm going to temporarily let x equal -3 and y equal 9 to solve for b. So what I get is 9 equaling 18 plus b. So ultimately b is -9. So that means the equation of the tangent, the thing that I was asked to find, is y equals -6x minus 9. If you have another way of finding the equation of a line, that's okay. Next one, let's use determine the derivative of that function there. So in this case, it'll be a slightly different formula. We'll say, instead of f prime x, we'll say f prime t is the limit as t goes to 0 of f of t plus h minus f of t all over h. And a quick reminder that if f of t is equal to the square root of t, then f of t plus h will be the square root of t plus h. A mistake a lot of people make is they say the f of t plus h is root t, and then they leave the plus h outside. That's not correct. In the function f, in this question right here, in that function, the input is under the square root. So if I use f of t plus h, the whole t plus h must be under the square root. Okay, so let's begin our solution. We've got our formula written there. So I say limit as h goes to 0, square root of t plus h minus square root of t all over h. If I sub in an h value of 0, I get the indeterminate form of 0 over 0. So I'm going to have to use my skills from the limits section. I can say the square root of t plus h minus the square root of t, and multiply that with the square root of t plus h plus the square root of t. And all of that is over h, but since I multiplied the numerator by a new factor, I must multiply the denominator by that same new factor. Okay, and now I can distribute here. The square root of t plus h times the square root of t plus h is t plus h. The square root of t plus h times the square root of t. Then I have negative the square root of t times the square root of t plus h, so they cancel out. And then I have negative square root of t times square root of t, so that's minus t. So what I get up top is t plus h minus t. And down below, I still have the same denominator I had a few moments ago. I can simplify that numerator. It's simply h. My denominator is h times t plus h, square root of t plus h plus square root of t. And now I can cancel out these factors. Remember, what we're doing when we cancel out is divide. So I'm dividing the denominator by h, and I'm dividing the numerator by h, so I'm leaving a 1 behind in the numerator. And so I can now plug in an h value of 0. I get 1 over the square root of t plus 0 plus the square root of t. Obviously, the square root of t plus 0 is the same as the square root of t. And the denominator root t plus root t is 2 root t. All right, so that is the derivative formula, f prime of t. This answers the question. F prime of t equals 1 over 2 root t. Okay, next question here. We're going to have to, as you now know, figure out what f of x plus h is. Even though this question never says f of x, it doesn't give me function notation. So I find it acceptable to just assume that's f of x. So I'll say f of x is 3x squared minus 7x plus 6. And then that would mean f of x plus h is 3x plus h quantity squared minus 7x plus h plus 6. Okay, so we'll use that information right now. We have the limit as h goes to 0 of 3 bracket x plus h quantity squared minus 7 bracket x plus h plus 6 minus 3x squared minus 7x plus 6 all over h. Now, x plus h quantity squared, we have to expand that out. That ultimately equals x squared plus 2hx plus h squared. So I'll put that in right here. X squared plus 2hx plus h squared minus 7x minus 7h plus 6 minus, I'm now going to distribute that negative sign here, minus 3x squared plus 7x minus 6 all over h. Okay, I'm going to distribute that numerator. We get 3x squared plus 6hx plus 3h squared minus 7x minus 7h plus 6 minus 3x squared plus 7x minus 6 all over h. And now we're going to simplify that numerator. The 3x squared terms kind of cancel each other out. This negative 7x and positive 7x cancel out. That positive 6 and negative 6 cancel out. So what I have is the limit as h goes to 0 of 6hx plus 3h squared minus 7h all over h. Now, if I plug in an h value of 0, I'll get 0 over 0. I'll get the indeterminate form, but at least now I've got it to a place where I can factor. So I'll factor out the h in the numerator. And I can now cross these factors out. And I'm now in a place where I can sub a h value of 0 in there. I get 6x plus 3 times 0 minus 7. I get 6x minus 7. So that's what f prime x equals. F prime of x equals 6x minus 7. This particular question said, determine the value of f prime x at x equals 5. So what they're really saying is, what does f prime of 5 equal? Well, that's 6 times 5 minus 7, which is 23. So the answer to this question is 23. Okay, next one here, we're going to determine f prime at 7 given this formula. And really quickly here, I'll just mention, you now know that we're going to have to figure out f of x plus h. So it's going to be 3 times x plus h plus 4. And that's going to be 3x plus 3h plus 4. I'm just going to put that in on the next slide when it says f of x plus h. So our formula for derivative is shown, and we can say the limit as h goes to 0 of square root of 3x plus 3h plus 4 minus square root of 3x plus 4 all over h. My limits work told me that I should multiply numerator and denominator by the conjugate of the numerator there. So I'm going to have square root of 3x plus 3h plus 4 minus square root of 3x plus 4 times the same two square roots, but with a plus sign in between. Okay. Now, what is that numerator going to equal? Well, the first square root times the first square root is going to give us 3x plus 3h plus 4. Then, when I expand that first radical times second radical, and then second radical times first radical, they'll cancel out. So I'm just going to be left with minus second radical times second radical. So that is minus the quantity of 3x plus 4 up top. That's equal to 3x plus 3h plus 4 minus 3x minus 4. And so ultimately what that equals is just 3h. So I'm going to call this the limit as h goes to 0 of 3h over h times radical 3x plus 3h plus 4. We didn't distribute the denominator at all, so we still have to write that in just the way it was. Okay? And now I can eliminate these factors, and I'm in a position where I can plug in an h value of 0. We have 3 over the square root of 3x plus 3 times 0 plus 4 plus the square root of 3x plus 4. This quantity right here, 3x plus 3 times 0 plus 4, is really just 3x plus 4. So really all we have downstairs is just the square root of 3x plus 4 plus the square root of 3x plus 4. That is equal to 2 times the square root of 3x plus 4. And so that is what f prime of x is equal to, this circled quantity up at the top with the star next to it. Well, this question asked us to determine f prime at 7. So f prime at 7 is going to be 3 over 2 times 3 times 7 plus 4. 3 times 7 is 21, plus 4 is 25. So I've got 2 root 25 in the denominator, which is another way of saying 10. So the answer to this question is 3/10. All right, let's do another one here. We know that f of x plus h will be 1 over x plus h. And we'll keep that in mind when we get to the next slide and begin our solution. We want to find the equation of the tangent line to that curve at the point where x equals 2. Well, in grade 9, we knew that in order to get the equation of a line, we would need a slope and a point. The point will be easy enough. The point will come about by taking this x value of 2 and plugging it into the formula for f of x. So the point's going to be 2 comma 1/2. But how do you get the slope? Well, the slope will be the derivative, whatever the value of the derivative is at x equals 2. So let's figure out an expression for the derivative. F prime of x is limit as h goes to 0, f of x plus h minus f of x all over h. So that's the limit as h goes to 0 of 1 over x plus h minus 1 over x all over h. In that numerator, up here, I have a common denominator of x plus h. So I can say the limit as h goes to 0 of x plus h over, oh, sorry, let me rephrase that. I can say we have a denominator of x plus h under each one of those fractions. So my first numerator will now be x. My second numerator will now be x plus h. And my denominator of the whole thing will be h. So up top, just look at what I've got up top. I've got x minus, this is the part I'm circling right here. I've got x minus the quantity of x plus h. So that's x minus h. So that's negative h. In my next line, I'm just going to call that negative h. Okay. So I've got the limit as h goes to 0 of negative h over x plus h. All of that is over h. Now, if you take this negative h over x plus h and you divide it by h, which is what this is telling us to do, that's really like saying multiply it by 1 over h. And so what we're ultimately end up getting is negative h over h times x plus h. So I'll write that in my next line. I've got the limit as h goes to 0 of negative 1 times h. That's what negative h equals. And then in the denominator, I've got h times x plus h. I can now cancel out these h's, and I can plug in an h value of 0. And so I get negative 1 over x plus 0. I'm plugging in this h value of 0 right there. So I get negative 1 over x plus 0, and that's the same as saying negative 1 over x squared. Okay. So at x equals 2, that derivative value, in other words, the slope of my tangent, that's going to be negative 1 over 2 quantity squared, which is negative 1/4. So the slope of the tangent line that I'm about to find the equation of is negative 1/4. I got that from subbing in that x value to the expression for the derivative. Grade 9 math tells me I also need a point on the curve. If you recall, we talked about that in the last slide before this one got so messy. We said the curve in question is f of x equals 1 over x. The point in question is where x equals 2. If I take an x value of 2 and plug it into the expression for f of x, I'll get the y coordinate of the point, which in other words is 2 comma 1/2. So basically, what it turns out I'm doing is I'm trying to find the equation of a line with a slope of negative 1/4 that extends through the point 2 comma 1/2. And I'm just going to see if I could squeeze in it at the bottom. This definitely got messy. but I've got y equals mx plus b, which means y equals negative 1/4 x plus b. And I can sub in the coordinates of the point 2 comma 1/2. So 1/2 will be equal to negative 1/4 times 2 plus b. So that means 1/2 equals negative 1/2 plus b. B ends up equaling 1. B equals 1. So that means the equation of the line that I was asked for in the question, the ultimate final answer to this question is y equals negative 1/4 x plus 1. Okay? And that's what it'll look like. That right there is a line that has a slope of negative 1/4 that extends through the point 2 comma 1/2. The equation is y equals negative 1/4 x plus 1. And that actually looks correct. That line looks like it's got a slope of about negative 1/4, and it definitely has a y-intercept of 1. So that's pretty cool. Now, in the next one, we're going to find the equation of a line perpendicular to the tangent of the graph at the point where x equals 2. A minute ago, we figured out that the equation of that the line in question, when I'm looking for the tangent, has a slope of negative 1/4 and goes through the point 2 comma 1/2. And when I use that knowledge, I get the equation of the line shown on that curve. Well, what this question is asking us for is the normal. So it's asking us to find out at the point 2 comma 1/2 what the equation of the normal line is. A normal line is perpendicular to a tangent line. So we know that so like I just said, we know the point in question is 2 comma 1/2. We know the slope of the tangent is negative 1/4. If I want to know the slope of a perpendicular line, I get the negative reciprocal. In other words, find the reciprocal, change the overall sign. So the slope of the line perpendicular to the tangent, i.e. the slope of the normal, will be 4. So therefore, I'm looking for a line with an equation of y equals 4x plus b that extends through the point 2 comma 1/2. In reality, what I'm looking for is the equation of that yellow line right there, the highlighted one. So it's pretty easy to find that out. We've done all the hard work. The slope is 4. I'm going to temporarily sub in an x value of 2 and a y value of 1/2. B ends up equaling negative 15 over 2. And so I can say the equation of that normal line, which I'll show you again, it's the yellow line on this curve that's perpendicular to the tangent. The equation of that line is y equals 4x minus 15/2. Okay, and finally, let's talk about the fact that sometimes we say that there is no derivative at a certain point. There's a verb called differentiate, and that means to find the derivative. And there's an adjective differentiable, which means a curve can be differentiated, i.e. has a derivative value at a given point. So you see 4 curves in front of you right there. All of those curves have a derivative value, i.e. are differentiable at every point on them. But each one has one exception. In this first question right here, in this first graph, right at the tip there, that red point, we say that that is not differentiable. When we get into graphing, we're going to see why that is. But we say that that's not differentiable and there is no derivative value. If it helps you to imagine why, just imagine how tough it would be to pick one tangent line for that point. It'd be pretty tough. So we say that when you have a cusp, the point of the cusp is not differentiable. There's no derivative value. We also have vertical tangents. If you look at this curve right here, the second one, this point that I'm drawing in red, if I had to draw the tangent, I would say that it looks something like this through that red point. Well, there is a tangent, and that tangent is vertical. But we learned in grade 9 that a vertical line has an undefined slope. And if the tangent's slope is undefined, we say the derivative does not exist. Another example is a discontinuity or a hole. Let's say we have a hole. Well, there's no derivative value at the hole because there's literally no point. If we had a piecewise function instead, let's say something that looks like this with a jump, we would say that there was no derivative value at that x value either, at the x value of the jump. And finally, if there's a corner such as y equals absolute value of x, we say that there's no derivative value at the point of the corner. Okay, so that is your lesson on derivatives.